In 1974, Saudi Arabia set up a special government body called the Saline Water Conversion Corporation, a group whose only job was to turn seawater into water people could actually drink. That single decision, made over 50 years ago, laid the groundwork for one of the most ambitious water systems ever built on Earth. Today, that early idea has grown into a giant steel network, stretching across the desert, carrying water from the sea to cities that would otherwise have almost none. Saudi Arabia is a huge country, but more than 95% of its land is covered in sand and rock, with rain falling so rarely that many towns go months without a single drop. The nation is home to over 37 million people, and almost everyone there follows Islam. Most of these people live close to the coasts, near the Red Sea on one side and the Persian Gulf on the other, while the middle of the country remains empty desert, too dry and too hot for anyone to settle. Underground, the country sits on top of more than 40 trillion litres of oil, making it one of the richest energy nations in the world. But no amount of oil money can make rain fall from a clear sky, and summer heat regularly climbs past 45 degrees Celsius, while yearly rainfall stays under 100 millimeters. Because of this, getting enough water for daily life is actually harder and more expensive for Saudi Arabia than pulling oil out of the ground. To solve this problem, engineers built a nationwide system of pipes that carries water from the sea all the way to cities deep in the desert. These pipes are made from strong carbon steel, the same tough metal used in oil and gas pipelines, because the water inside travels under heavy pressure, and the pipes themselves must survive being buried underground through blazing hot days and cold desert nights. Laying just 1 kilometer of this pipeline costs around $3 million, and that price does not even include the pumping stations that push the water along, or the massive plants that clean the seawater in the first place, each of which can cost tens of millions of dollars to build. Since there is no shortage of seawater nearby, engineers turn to the ocean itself as their main water source. Building a pipeline that stretches across an entire desert nation starts long before anyone starts digging. It begins in a factory, where flat rectangular sheets of steel are cut to exact sizes needed to form large pipes. These sheets are then fed into a machine with many rollers that slowly bend the flat steel, curling it step by step until the two edges meet and form a round tube shape, roughly 1.8 meters wide, with walls almost 25 millimeters thick. Once the shape is right, workers weld the seam running along the length of the pipe to close it completely. Right after welding, the hot seam passes through a cooling line filled with flowing water to bring its temperature back down safely. Workers then grind down every rough edge and corner on the pipe to remove sharp bits of leftover metal and make sure the shape is accurate. Both ends of each pipe get a slanted cut called a beveled edge, which helps two pipe sections fit together neatly and weld cleanly when they're eventually joined out in the field. Each finished pipe section usually measures about 12 meters long, a length chosen carefully because it cuts down on the total number of joints needed, while still being manageable to load onto trucks and haul across long distances. Once the pipes are ready, they get moved to open storage yards, where they're stacked in groups and labeled clearly so workers can keep track of every batch. From there, cranes or forklifts load them onto special trucks built to carry such large, heavy loads, and everything gets strapped down tightly so nothing shifts or bends during the drive. The trucks then travel hundreds of kilometers across the desert to reach the actual construction site, where the real work of joining everything together begins. Before any digging starts, survey crews walk the planned route using GPS devices and other precise measuring tools to map out exactly where the pipeline will go. They mark the path on the ground with stakes and paint, carefully choosing a route that avoids soft, shifting sand and areas where the ground could easily erode or collapse. Getting this route right matters enormously, since even a small mistake early on could cause serious structural problems years down the road. Workers then clear and flatten the land along this path so heavy machines can move around freely. And they build temporary dirt roads next to the pipeline route so trucks, diggers and welding crews can reach every part of the job. In such a dry, dusty environment, controlling blowing sand and keeping the air breathable for workers becomes its own ongoing task. With the path cleared, large tracked excavators start digging a long trench following the marked route, cutting it to just the right width and depth to hold the pipe and leave room for covering it back up later. As dirt comes out of the ground, workers sort it on the spot, keeping soil that's good enough to reuse for filling the trench back in later, while getting rid of anything unsuitable. Keeping the trench depth even along its whole length matters a lot, since any dips or bumps could bend or crack the pipe once it's lowered in. In some stretches, the pipeline has to cross rocky mountains, where digging machines simply can't cut through solid stone. In these tough spots, crews use carefully placed explosives, setting off controlled blasts in sequence to break apart the rock and carve out a trench deep enough to bury the pipe safely, even in places where no machine could ever dig. Once a trench is dug, workers don't just drop the pipe straight onto the bare dirt floor. Instead, they spread a smooth layer of fine sand or screened soil along the bottom first, creating a soft cushion that spreads out the weight of the pipe evenly and stops pressure from building up in any one spot. This cushion gets leveled and gently packed down to the right height, and it turns out to be especially important in desert areas, where the natural soil is loose and dry and can't support weight on its own very well. For the biggest sections of pipeline, crews first clear a wide work path about 40 meters across, allowing trucks, machines and workers to move continuously along the route at a steady pace of roughly 1.5 kilometers finished per day. The pipe sections used here stretch about 18 meters each, a length picked to cut down on the number of welds needed, though moving and lining up such long, heavy pieces takes serious skill and careful machinery. At the point where two pipe ends meet for welding, workers use a hydraulic clamp fitted inside the pipe that expands outward in every direction, gripping the metal firmly and holding both pieces perfectly lined up before the first weld pass even starts. A team of around 80 skilled workers, supported by dozens of automated welding machines, can finish as many as 150 welded joints in a single day, on pipes measuring 42 inches across. After each weld cools, machines send sound waves through the metal in a process called ultrasonic testing, checking carefully for any hidden cracks or weak spots inside the joints that eyes alone could never catch. Once a weld passes inspection, another crew blasts the area with fine abrasive material to clean the surface completely, then coats it with a thick liquid epoxy that hardens into a tough, sealed, protective layer, shielding the metal from rust and damage before it ever goes underground. Getting the finished pipe strings safely into the trench takes its own specialized machines, called side boom tractors, which are tracked vehicles built specifically to lift and move long pipelines. Several of these machines work together in a line along the pipe, each one lifting a section using padded slings and steel cables designed not to scratch or damage the protective coating. Together, they raise the entire pipe string smoothly off the ground and hold it steady in the air while slowly rolling forward along the trench. This part demands extremely careful teamwork between every operator, since even a small mistake could twist the pipe, bend it out of shape, or scrape it against the trench walls. Once everything lines up correctly, the crew lowers the pipe down bit by bit until it settles gently onto the sand cushion waiting at the bottom of the trench. The whole time, surveyors keep watching the pipe's position, checking that it stays straight and doesn't bend unnaturally, since any leftover stress in the metal could weaken it over time. This lifting and lowering method works especially well for long, straight stretches of flat desert, letting crews place pipe quickly while keeping accuracy high. After the pipe finally rests in the trench, workers fill the space back in, using several layers of material rather than dumping everything in at once. The first layer going in is soft and fine, protecting the pipe's outer coating from getting scratched by rocks or debris. And only after that does the previously dug up soil go back on top. Each layer gets packed down firmly by machines before the next one goes in, since loose soil could sink or shift later and cause the ground above to sag. In a desert climate, where soil constantly deals with strong winds and huge temperature swings, packing every layer down properly makes a real difference in how long the buried pipeline lasts. Getting water from the sea to the treatment plant starts with a separate line of pipe running from open ocean water toward the shore, forming the very first step of the whole system. Workers first place large sections of intake pipe out at sea, carefully lining each piece up before lowering it into position using powerful cranes mounted on barges or floating platforms. As the line stretches closer to land, crew members connect each new section in order, building one continuous tube strong enough to handle constant water pressure flowing through it around the clock. Getting every joint perfectly aligned matters enormously here too, since even a tiny gap or bend could hurt how well water flows through later on. Once the whole intake line is finished, workers add extra support frames around it and anchor it firmly to the ocean floor so it stays put no matter how rough the sea gets. Inside the treatment plant, the whole cleaning process starts by pulling seawater in through openings positioned a few hundred meters offshore, where sturdy barriers and screens stop floating trash and keep sea creatures from getting sucked into the system. A single intake pipe measuring 63 centimeters across can pull in as much as 15 million liters of water every single day, which works out to more than 10,000 liters flowing in every minute. Strong pumps stationed right at the intake point push all that seawater forward into the plant for treatment. Naturally, along with the water come uninvited visitors like jellyfish, small crabs, and the occasional fish. So a large screen catches anything bigger than 4.5 millimeters right away, followed by a second, finer screen that traps whatever smaller debris slipped through the first one. Even after both screens do their job, the water still carries plenty of tiny floating particles, too small to be caught by any screen. To deal with this, the water flows down through tanks filled with layers of sand, a method called filtration, where the tiny gaps between sand grains let water pass through freely while trapping solid particles against the grains. This sand keeps shifting slowly in the opposite direction the water moves, carrying trapped dirt away as it goes. Once the water finishes this stage, it looks noticeably clearer, but it still contains particles far too small to see, some measuring roughly 1/10 the width of a human hair. To catch these leftover specks, large paddles stir the water while two chemicals get mixed in: a disinfectant called sodium hypochlorite and a substance called ferric chloride that makes tiny particles stick together into bigger clumps. These heavier clumps then sink to the bottom of the tank on their own, pulling most of the remaining dirt out of the water, though it's still not clean enough yet for the final drinking water stage. From here, the water flows into cartridge filters, considered the last line of defense before the most important step of all. Each filter housing holds several cartridges made from tightly packed fiber material, with gaps as small as 1 to 5 microns, smaller than almost anything visible to the naked eye. Water pushes from the outside of each cartridge toward its center, leaving behind any remaining tiny particles caught between the fiber layers, while clean water continues onward. Whenever a cartridge fills up with trapped debris, workers simply swap it out for a fresh one to keep the whole system running at full strength. Now comes the hardest part of the entire process: pulling the salt itself out of the water. Salt is stubborn to remove because salt particles bond tightly to water molecules through natural electric attraction, meaning the only way to separate them is by applying serious pressure. This step is called reverse osmosis, and the idea behind it is fairly simple, even if the engineering is complex. Push water hard enough against a superfine membrane that water molecules squeeze through while salt and other unwanted substances get left behind. Powerful pumps generate this pressure in stages, each one boosting the pressure a bit further than the last, until by the final stage, the water reaches roughly 60 times normal atmospheric pressure, more than enough force to rip water molecules away from the salt clinging to them. After passing through this first round, the water is already mostly free of salt, but tiny traces of minerals and ions still remain, enough that it wouldn't quite meet safe drinking standards yet. So the water passes through a second round of even finer membranes, this time running at somewhat lower pressure, but doing an even better job stripping out whatever ions are left. By the end of this second pass, the water reaches an extremely high level of purity, ready either for further treatment or straight use. Interestingly, water this pure isn't actually ideal for drinking right away. Its acidity level needs adjusting first, usually done by adding a small, carefully measured amount of acid or a balancing chemical to bring it into a safe range for human consumption. On top of that, since reverse osmosis strips out virtually every mineral along with the salt, plant workers add back small amounts of calcium and magnesium during a step called remineralization. This final touch restores some natural taste to the water, adjusts its acidity properly, and makes it noticeably healthier and more pleasant to drink than plain, stripped-down, purified water would be on its own. Once every step finishes, the clean water finally leaves the plants and travels through the very pipeline network described earlier, eventually reaching taps in homes and businesses across the country. All of this comes at a steep price though, with each cubic meter of desalinated water costing around $5 to produce, compared to just a few tens of cents for the same amount of water in places like the United States. It's a striking reminder that turning an ocean of salt water into something safe enough to drink, farm with, and build an entire modern nation around is neither simple nor cheap. Yet Saudi Arabia has managed to pull it off anyway, one buried steel pipe at a time.